Hello and welcome to Podcast.init, the podcast about Python and the people who make it great. When you're ready to launch your next app, you'll need somewhere to deploy it, so check out Linode. With private networking, shared block storage, node balancers, and a 200 gigabit network, all controlled by a brand new API, you've got everything you need to scale. Go to podcastinit.com/Linode to get a $20 credit and launch a new server in under a minute. To get worry-free releases, download GoCD, the open-source continuous delivery server built by ThoughtWorks. You can use their pipeline modeling and value stream map to build, control, and monitor every step from commit to deployment in one place. And with their new Kubernetes integration, it's even easier to deploy and scale your build agents. Go to podcastinit.com/GoCD to learn more about their professional support services and enterprise add-ons. And visit the site at podcastinit.com to subscribe to the show, sign up for the newsletter, and read the show notes. Your host as usual is Tobias Macy, and today I'm interviewing Tom Augspurger about the extension interface for Pandas data frames and the use cases that it enables. So, Tom, could you start by introducing yourself?
Yeah, so I have a somewhat common, I think, background at least for scientific people. I was in economics grad school, needed to pick up something for doing data analysis, some kind of programming language. They started us with MATLAB, which was not my favorite, and eventually I made my way over to Python, learned Pandas, started contributing to Pandas, and that's essentially where I got to where I am today, which is data scientist / software engineer for Anaconda, working on open source tools for data analysis.
And do you remember how you first got introduced to Python?
I think so. I had a friend who was into programming languages just in general, wrote his own iOS apps. He was in the accounting program. I was in economics. He guided me towards either R or Python. And in the end, he recommended Python because R's assignment character is 2 characters long. Instead of just an equal sign, they use less than minus. So that trivial detail led me to Python, and I've been really happy with it ever since.
That's an interesting criteria to base your language choice off of. It's an extra character. It's going to take a lot of time over the years.
Yeah. I think RStudio has a short keyboard shortcut to make it a single keystroke anyway, but yeah.
Yeah. And so most people are fairly familiar with the Pandas library and some of the capabilities that it brings along, but can you give a high-level overview of the new extension interface that you've added?
Sure. So for some background, Pandas has a data frame. It's a container for tabular data like you might find in an Excel spreadsheet or a database table. And internally, Pandas uses NumPy to actually store the data. So there's a whole bunch of NumPy arrays behind a Pandas data frame. So the key difference between NumPy and Pandas is that NumPy provides n-dimensional homogeneous arrays, whereas Pandas is really focused on the 1 and 2 dimensional case. But the trade-off there is that Pandas is able to support heterogeneous data. So a NumPy array has a single data type for everything, whereas a Pandas data frame has a single data type per column. So with the Pandas data frame, you can have a column of ints, a column of floats, a column of strings, date times, whatever. Okay, so internally, you can have NumPy arrays, which provides the basic types like floats, ints, booleans, date times, those sorts of things. But Pandas users have a few different use cases than NumPy. NumPy came out of more like the physical sciences. It's very popular in astronomy. So you're dealing with a lot of floating point data, these sorts of things. Pandas users want to deal with a richer set of data types often. So we've made some extensions to the NumPy type system internally. One of the most notable ones is the categorical D type, where you have your array's values can only come from a fixed set of categories. So if you think about survey data, this is, do you strongly agree, all the way down to the scale of strongly disagree. There might be 5 categories that your values can come from. So we wanted to support these kinds of uses within Pandas, but it was too difficult, or NumPy didn't want these types of extension D types that we've been making. So internally to Pandas, we hacked in a few places these extension D types like categorical or date times with time zones, or intervals for, is this data in this interval like you might find in Postgres. So we had these internal extension types, and we wanted to essentially make that easier for people to do outside of Pandas, to basically say, hey, I have this array type. It's not a simple NumPy array, but it's similar enough that it can be stored in a data frame.
And so my understanding is that for the impetus for creating the new extension interface, there was a customer who wanted you to add it directly into Pandas, and when you brought that proposal to the community, it was rejected in favor of this new API. So wondering if you can just give a bit of the background behind how this new interface was started and maybe some of the challenges associated with building it.
Yeah, so Anaconda does some consulting and a lot of open source development too. So they're kind of in this nice position to tie together businesses and research institutions that have these use cases that maybe they can't share or they don't have the connections within the open source community to propose directly. So they came to Anaconda with this need where they had IP address data in a tabular data set. So one of their columns in their data set contained IP addresses. I wrote up a proposal to Pandas, tried to do some research on how prevalent IP addresses and this kind of networking data is within the community, whether people were asking around for it. And there was some interest for it on Stack Overflow and various other issues. But eventually we decided that it was too niche, too type specific for this small community. So we didn't want to include it in Pandas proper. But like I said, we had these extension D types internal to Pandas that we had kind of hacked together in a few places. So we decided we wanted to support these use cases outside of Pandas by providing the necessary hooks.
And prior to adding this new ExtensionArray interface, what was the option for people who wanted to be able to extend the functionality of Pandas or add new data types?
Yeah, so you always have the fallback of storing your objects, your arrays as Python objects. So NumPy can store anything. It just won't be as fast when it's storing Python objects. So if you were dealing, in this case, with IP addresses, you might store them as either an array of strings representing the IP addresses or perhaps an array of IP address objects. So Python 3 has an IP address module that provides IPv4 and IPv6 objects for scalar types. And if you wanted to store an array of them, well, maybe you would just store an array of those objects. The downside to that is that, first of all, it's going to be a lot slower. So once you have Python objects, you're not really able to lay them out in a nice memory efficient layout like NumPy is able to do with the basic types like ints and floats and so on. So it's going to be slower, and it's also going to be error prone, because if you want to do something like give me all of the columns that contain IP addresses, Pandas has a select D types function where you say, I want all of the floating point columns or all of the integer columns. You can't do that with object columns because there's no way to know that all of the object columns are they're actually containing IP addresses. You'd be mixing in potentially other columns there. And then it's also, you have to do all your own logic on processing those. So those would be kind of having to reinvent a lot of the stuff that Pandas is already knows how to do on array-like objects.
And there's another project that's based off of Pandas, I believe it's called XArray, that allows for multi-dimensional data frames, essentially. And with this new ExtensionArray interface, will that also propagate to that other library for being able to do these n-dimensional tables and being able to use these new data types within them?
I don't think so. I haven't used XArray greatly, but as far as I know, XArray is the actual data themselves need to be limited to homogeneous n-dimensional values. So the data inside an XArray data set is an actual NumPy array, which is still going to be limited to those basic types, and it does have to be homogeneous, a single data type, even if you have multiple dimensions. What XArray will benefit from is, in the future, we'll be able to have these kinds of extension index objects. So that hasn't been implemented yet, but Pandas has the idea of the columns of a data frame where you can store a NumPy array, or now this extension array type, or an index, which is used for like looking up values. So Xarray uses Pandas indexes directly. And then in the future version of Pandas, once we're able to support these kinds of extension array types in the indexes, Xarray will gain that as well.
I know that when you were first building this, there was a particular data type that you had in mind for being able to support IP addresses natively, but what are some of the other new data types that are available as external packages?
Yeah, so the IP address use case is now being served by a library called CyberPandas, which I think is a pretty great name. So that's going to be providing the IP array, and then they also wanted to work with MAC addresses. And I should say, up front, just to give more concrete use case here, the reason we can't store IP addresses just as integers is because our client was interested in working with both IPv4 and IPv6 addresses. And IPv6 addresses require 128 bits to store, which NumPy does not provide a 128-bit integer type. So the way we're doing this internally in CyberPandas is storing a NumPy structured array, which is going to have two fields, one for the lower 64 bits, and then a second field for the upper 64 bits. So we're essentially tricking Pandas into thinking that this 2D object with these two fields is actually a one-dimensional thing. So that's CyberPandas. It's doing the IP address and MAC array specific things. So there's also GeoPandas, which is a Pandas-like library. It actually subclasses a Pandas data frame right now. But one or more of the columns contain geographic objects. So these might be things like lines or segments or boxes, things you might find in a GIS library. And on the CyberPandas master has a refactor to do a whole bunch of these geographic operations in Python, which will speed things up quite a bit. The way it's doing that is by instead of storing Python objects with the geometries, it's going to be storing pointers to C structures that have all the geometry information. So it's just an integer that represents some pointer. In CyberPandas master, they had to do some pretty bad hacks into Pandas internals to try and get what is actually an array of integers to be treated as a special column. But with this extension array interface, it's going to be quite a bit cleaner for them. Those are the only two public ones I know of. There's a contributor to Pandas who's doing something internally for their company, but it is quite new. So I'm hoping that we'll have quite a few of these packages popping up for domain-specific uses.
And one of the other nice things about having this unified interface is that rather than having to create these various subclasses that won't necessarily play nicely together, you just have this one interface so that you can, for instance, maybe have an IP field along with the geographic information so that you can actually join the IP address with maybe the return value of a GeoIP lookup within a single data frame rather than having to have these conflicting implementations and try and choose one versus the other, or maybe instantiate them separately and then have to do a join across them or something like that.
So GeoPandas currently uses a subclass of the data frame, which is fragile. In our documentation, we warn against it because it's hard to do properly. And like you said, being able to combine these different kinds of extensions just doesn't work when you're subclassing. But now that we have the interface within Pandas, we also have an extension accessor API where people can say, hey, Pandas users know about this already with categorical. So when you have a categorical column, you can type .cat, and then under that namespace, there's a whole bunch of categorical specific properties. So we'll be able to do the same thing with CyberPandas. Registers the .ip namespace on the data frame. GeoPandas does .geo, so these various packages will be able to work together much better.
And are there any other unique use cases that this extension interface will enable, or any of the current or upcoming implementations will allow for beyond just what the core Pandas project provides?
Yeah, so we kind of always had the fallback of storing things as Python objects. So you could usually achieve what you want to do by just storing your values, your scalar values as Python objects. But like I said, that's going to be quite slow compared to a more optimized implementation. So you'll be able to analyze larger data sets more quickly by having an optimized extension array implementation. And I think combined with the new extension accessor API, where you can say, .ip or .geo, it's going to be quite natural to Pandas users to be able to, install CyberPandas and then just start analyzing IP address data like they would any other data type.
Does this implementation work nicely with the Arrow library for being able to translate Pandas data frames back and forth between R using the Arrow serialization format?
Yeah, so that's actually one of the use cases that we're going to be prototyping next. There's an Arrow and Pandas contributor who's interested in prototyping storing strings as Apache Arrow arrays instead of currently Pandas uses a NumPy array of objects for storing strings. So this is going to be really helpful for prototyping these sorts of things within Pandas. And then there are broader visions of an Apache Arrow back Pandas data frame. I'm not sure exactly what that's going to end up looking like, but being able to drop these pretty simple implementations in as extension arrays will be certainly helpful for testing those out.
And you've discussed a bit about the fact that the new extension array allows for being able to store these values as alternative implementations beyond just NumPy. So I'm wondering if you can dig a bit more into the implementation details of how you built the interface and what have been some of the most difficult aspects of that, particularly with needing to be able to maintain some of the same API interface for the Pandas data frames.
Sure. So for an extension array author, there's two base classes that we provide, an extension D type and an extension array, that they're abstract base classes. We don't actually inherit from ABC Meta because that makes is-instant checks really slow. So we had to remove that. But there are these base classes with some abstract methods that you provide as an extension array author. You provide information on what your scalar type is. So for CyberPandas, my scalar type is an IP address object, either IPv4 or IPv6 object. You say, what is your missing value sentinel if you have one? So like the IP address 0 is going to be treated as missing in Pandas operations, like an is_in_a or fill_in_a. And then, various other array-like things like how do I compute your length? How do I slice you? How do I copy you? These various array-like things are required by the implementation author. We also provide some defaults, things like fill_in_a and finding the unique values. It's assumed or required that your extension array can be convertible to a NumPy array, even if it isn't actually a NumPy array natively. But by converting from your specific storage type to a NumPy array, we can provide default implementations like fill_in_a and unique and factorize. It's just probably going to be slower than you could do on your own. So a good example of this is like if you have a GPU-backed array. I think when we met at PyCon, I was prototyping with Sue, who also works at Anaconda, on getting a CuPy-backed array inside of a Pandas data frame. So as I understand it, GPUs are able to sort data extremely quickly. So you might not want to rely on the default sorting implementation by, converting your CuPy array to a NumPy array, then sorting, and then converting it back, since there's a bottleneck transferring from the GPU to the CPU and back again. But if you're able to override the method for sorting, then you can use the fast CUDA sorting kernels, and things will be super quick. As far as some of the challenges, you really hit up on it. It was so Pandas is a large library. It has some crufty corners, I guess. Part of the motivation here for implementing this extension array interface was to clean up our own internals. I think we had essentially reinvented this type of stick this not quite a NumPy thing inside of a data frame or a series. We had reinvented that like 3 or 4 times, slightly differently each time. So we were able to clean up quite a bit by having this single clean implementation about what it means to have a NumPy thing or a non-NumPy array-like thing inside of a data frame. So that was the hardest one, was definitely preserving backwards compatibility and avoiding edge cases around that. Fortunately, we have a lot of tests in the Pandas codebase. Other than that, it was tricky from an API design standpoint. We're being quite deliberate about not inventing a new array type. We want to, we're not replacing NumPy here. The idea is to be able to take array-like things without imposing any restriction on the actual storage of the data. So trying to design an API around how to do array operations on this kind of abstract notion of data, of just an array decoupled from any storage, was an interesting challenge. And then another kind of interesting fun one was being able to design tests that could be reused in other libraries. So we made these essentially base classes for tests, and you provide PyTest fixtures for inserting your own data into that. So CyberPandas is providing a fixture to generate some specific IP address data that is then run against the tests that we are using to verify correctness and are you conforming to the expectations of the interface.
And what are some of the limitations imposed by the new interface for any libraries that want to add new functionality? And have you had anyone who's come up against those limitations and wanted to be able to add new capabilities, and wondering how that conversation may have gone?
Yeah, there are definitely some. This is the minimum viable implementation, I think. We were overdue for a release, so we had to get things together and cut things off at some point. So some things like operations just don't work. So if you compare two extension arrays, do like equal, I hope it throws an error. I'm actually not sure what happens right now because it's just not implemented. So operations are definitely not done, and that's being worked on right now, actually. And then there's a whole bunch of other, Pandas data frames have a ton of methods. We did the common ones. So again, thanks to Anaconda, we had a concrete use case in mind. Our customer had use cases that they needed served. So we had a good example, and GeoPandas provided a secondary thing to check out, okay, what all needs to be implemented for a reasonable set of analyses to be possible. But other ones just haven't been dispatched to yet. So things like isIn currently will not do the correct thing, checking whether the array of values is in this other thing, is in this other array. That's currently not doing the correct thing. So there will be a whole long tail of methods that need to be added to the interface. But, the most basic ones are served right now, I think.
And you've touched briefly on some of the next changes that you want to be able to bring in for the extension array, but are there any other major changes or improvements that you'd like to see added in Pandas to make it easier to use and extend?
Yeah, so the biggest one that Jeff Reback, who's one of the maintainers of Pandas, has pull request open right now, adding integer missing value support to Pandas. So a bit of background on missing values. Currently, Pandas uses numpy.nan, so nan is a floating point value, and we use that to represent missing data, even for integers. So the unfortunate consequence of this is if you have an array of integers, but even one of the values are missing, then your integer column suddenly becomes a float. And this causes all sorts of headaches. So we have a PR open right now adding integer missing value support by default. So in the next version of Pandas, it'll just be a thing that you can opt into, and we'll have to figure out a path forward for getting that to be the default behavior when missing values show up in integer columns. But that's going to be solving like one of the longest standing pain points within Pandas. We also, so I think I mentioned earlier, Pandas uses object dtype for storing strings. So strings are currently stored as a NumPy array of objects. That's painful for several reasons, but the biggest one is just speed. So being able to have a dedicated string type will be really nice for the speed improvements and all the nice ergonomics that comes with having a specific type for some type of data. Another one is, this might be too in the weeds, but So we have a categorical D type. That currently serves kind of two purposes. We have the original intent is for this type of data that can come from a fixed set of categories. So you have these from strongly disagree to strongly agree. Where are you on that scale? It's also serving a secondary purpose as a memory efficient container for data that has low cardinality. So this is, if you have like string data where there's only a relatively few number of unique observations. So if you have the population of the United States and you're storing the state as, the 2-letter code for each state, then that's going to take a ton of memory. But if you store it as a categorical, it's going to be quite a bit more memory efficient. We're going to be adding a dedicated type for this type of interned string that will have the memory benefits without the kind of the categorical fixed set of categories, semantics attached to categorical. So that's within pandas. External to pandas, like I said, there's cyber pandas providing IP types. GeoPandas is going to be a really nice speed improvement there. I spoke to a person who's doing medical research. They have MRI data. And so they're dealing with these tabular data sets, but one of the fields are these actual images. And they want to be able to tie their analyses to that image. So essentially treating an image as a single column in the data frame, but be able to do some image-specific operations on that image data without necessarily loading it into memory ahead of time. It'd be loaded in on demand. That'd be a pretty cool use case, I think. One really cool one to see would be better nested data support. So where a column is either an array or some nested thing like a dictionary or dictionaries of dictionaries, being able to better support that, both storing it in a more memory efficient format than what pandas would currently do just as objects, and also an API for working with that data that might look like JQ, which is a command line tool for parsing JSON objects. Being able to better support nested data would be really nice. I'm not sure if that belongs in pandas or outside pandas, but we'll at least be able to see it.
And so Pandas was originally inspired by some of the data frame interface available in R, and since then there's also been data frames added to Spark. So I don't know what the current landscape looks like as far as having a unified definition of what a data frame is and does between these different languages and runtimes.
Yeah, so two things there, I think. So first of all, Apache Arrow is kind of trying to be the in-memory format for how to store data, tabular data anyway, across these various systems. So being able to have a column that is backed by an Apache Arrow array and then serializing that and getting it to the JVM for use in Spark is like a major goal for Apache Arrow. I should say Apache Arrow is being worked on by Wes McKinney, who is the original author of Pandas. So he cares a lot about this. The ExtensionArray interface is going to allow us to really quickly prototype with what that would look like from the Pandas side of things. So it'll definitely help out with being able to have these alternative memory storage formats within Pandas. So that kind of leads to the second idea, which is these kind of foundational libraries like Numpy and Pandas being about the nice APIs that they provide and less about the actual memory implementation. So this is an ongoing discussion within Numpy is how do you take these things? You have various array implementations, NumPys being the first one, but also things like CuPy providing a NumPy-like implementation on the GPU. So how do you write code if I want to take like the logarithm of every element in an array? I would do that personally by writing np.log and then passing it the array. But if I want to write a library that supports both NumPy arrays and CuPy arrays, I suddenly have to add in this compatibility layer to be able to support both. It'd be nice if your code like np.sum or np.log is able to dispatch to the correct implementation for that actual physical array. So this has been going on. This is like the array ufunc protocol helps out with a lot of it, but we're kind of pushing that forward both on the NumPy side, and then I'd like to see it happening on the Pandas side as well.
And do you see any movement in the other language communities to try and work with pandas or work with each other to create a sort of common denominator implementation or API so that it's easier to translate analytics code between various runtimes languages?
That one I'm not sure about. I know Apache Arrow wants to provide the memory format, and I think that Wes is interested in writing kernels, so like these kind of math operations. How do you take the sum over an axis of an array? He's also interested in doing that, and then being able to share that amongst various runtimes is a major goal of Wes's, to avoid all this kind of wasted effort of each language community having to do their own implementations of everything. Is kind of, it's unfortunate, I guess. So I'm not sure where things are at on that.
And are there any other areas of discussion related to this topic that you think we should cover before we start to close out the show?
I think kind of in the theme of making these libraries more about their APIs and less about their actual implementation, I would like to, when we find the time, make Pandas plotting essentially configurable to use various backends. So Python is fortunate to have tons of libraries, like matplotlib being the most notable, for visualization. And Pandas plotting is currently built into matplotlib. It constructs these matplotlib objects. But we also have libraries like Bokeh and now Altair, and I'm sure others that I'm forgetting about that provide other plotting backends. So it'd be nice if we could take the same Pandas plotting API, which is great for quick, throwaway plots to quickly visualize your data, but have it show up in your backend of choice so that you can do further adjustments afterwards. We've got a small little prototype of that, but I'd like to flesh that out and make it an actual thing.
So for anybody who wants to follow the work that you're up to and keep in touch, I'll have you add your preferred contact information to the show notes. And so with that, I'll move us into the picks. And for my pick this week, I'm going to choose the Black Panther movie. I watched that recently and, had been hearing a lot of good things about it, and I was happy to see that it lived up to most of them. So it's definitely a fun movie, worth it if you're into any of the Marvel superhero films. And so with that, I'll pass it to you, Tom. Do you have any picks this week?
Yeah, kind of a selfish one, but I'm going to be picking a library called DaskML. So this is a Python library for doing scalable machine learning. And it's a bit selfish since I'm working on it right now, along with some others, just trying to explore what it means to do large-scale machine learning within Python. So things like fitting a scikit-learn model on a cluster. If that sounds interesting to you, check out Dask, which is the kind of parent project that this falls under, and then DaskML for machine learning specific things.
Dask is definitely an interesting project, and that reminds me that one of the other things I wanted to follow up on with this discussion is whether the extension interface for Pandas is going to be reflected within Dask and being able to parallelize operations on these data frames.
Yeah, so we're discussing that right now. Basic things do work without any changes to Dask. There are a few other things that we think we could guess on the Dask side of things, but we think it would be better for the ExtensionArray authors to explicitly opt into it. So things like Dask sometimes needs a small sample data set of your array. We could guess at that by looking at the first few values within Dask, but we think it'd be better for the library authors to opt into that, essentially. So things work basically well, at least for CyberPandas, and for GeoPandas, we've played around with a scalable version of GeoPandas built on top of Dask as well. Those both work since I think they're using NumPy arrays under the hood, but being able to properly support them will take a bit more work.
All right. Well, thank you for taking the time today to join me and discuss the work that you've been doing and for adding in this new functionality to Pandas. I'm definitely interested to see where it takes us. And so I want to thank you for that. And I hope you enjoy the rest of your day.
Thanks. Nice talking to you.